Hi everyone. Today let's talk about session 13.1, Systems of ODE. So last time we talked about how to solve first-order ordinary differential equations. We have the Euler's method and the modified Euler's method and the Runge-Kutta method. So in this session, we'll extend the techniques we talked about last time to the higher order ODEs and systems of first order ODEs. First, let's see how a higher order ODE can be converted into a systems of first order ODE. So suppose we have a second order ODE, y double prime equals a function of x, y, and y prime. Okay, so we can convert this higher order ODE to two first order ODE by letting u be y and let v be y prime. Then u prime is y prime, which is v, and v prime is y double prime, which is g of x, y, and y prime. But now x is still x, y is u, y prime is v. Now we get, so here I should change this to u and change this to v. Oops. Now we have a systems of first order ODEs. The initial conditions for the original ODE, y of 0 is a0, y prime of 0 is a1, then it becomes the initial conditions for the systems. U of 0 equals a0 and v of 0 equals a1. Okay, so this is second order ODE. So we create two new variables u and v, and then we can get a system of first order ODE. So in general, for nth order ODE, we're gonna create n new variables. Okay, we let u1 be y, u2 be y prime, so u1 be y, u2 be y prime, and un be y to the n minus 1 derivative. Okay, then we get u1 prime is u2, u2 prime is u3, The last one, un prime is g of x. Here I also changed this. So this is g of x, y prime is u1, and then y is u1, y prime is u2, etc. And we have un. So far so good. And we also changed our initial conditions. So this is how we can convert higher order ODEs into system of linear ODEs. So now if we know how to solve system of ODEs, then we also know how to solve higher order ODEs. Okay, so let's look at the following example. We want to convert the following higher order ODE into system of first order ODE. So usually if there are two variables or second order ODE, then we can use u and v. But if the order is higher or equal to 3, then we start to use the subscript u1, u2, u3. Okay, so here we can let u1 be y, u2 be y prime, and u3 be y double prime, right? Then u1 prime is y prime, which is u2, u2 prime is y prime prime, which is u3, and u3 prime is y triple prime. That equals, so we solve for y triple prime in the differential equation. So we move all the terms to the right hand side except the y triple prime. So we have xy double prime minus xy squared minus e to the x. Okay, so this is our system of first order ODE. 2 prime is u3, u3 prime is xy double prime. Oh, so y double prime is u3. And then y is u1. Okay, so this is what we get. And also the initial condition u1 of 0 is y of 0, which is 1. u2 of 0 is y prime of 0, which is minus 1. u3 of 0, sorry. u3 of 0 is y double prime of 0, which is 2. So far, so good, everybody? Okay. And you can see the special is for the previous n-1 equations, we have ui prime is u sub I plus 1, right? And the last equation is related to our differential equations, the given differential equation. Okay, let's continue. So now it's enough to learn how to solve systems of first-order ODEs. Let's first talk about the Euler's method. Do you remember for the first-order ODEs, we talk about Euler's method and Wunsch-Koetter method. So in session 13.1, we will talk about the Euler's method in session 13, and then in session 13.1.3, we will talk about the Wunsch-Koetter methods for systems of ODEs. Okay, so to apply the basic Euler's method, we have yi plus 1 equals yi plus h times the slope, which is f of xi yi. Now we want to apply this to the following systems. Okay, let's say u1 prime is f1, u2 prime is f2, and un prime is fn. Okay, so u1. Okay, so here, the subscript is the index of the coordinates. Okay, so this 1, 2, n, they are index of the coordinates. Okay, and the I in the parentheses. So this is I plus 1. They are the index of the iterations. Okay, the steps. So far, so good? Yeah, we went out of the index because I was thinking about to move these index on the top, but think about it, the top looks like square. And even though I can put parentheses, but parentheses means this is like derivative. So I know if we put it inside this I plus 1, this is the index, but it looks like this is the number we're plugging for x. But this is not true, okay? I know there is abuse of notation here, so I ask everybody to be careful about that. So far, so good, everybody? So things in the parentheses, they are not the x values. They are the index of the iterations. The x values is x of I. This is xi, right? Okay. So similarly, see we have yi plus 1 is yi plus h times the slope. Here we have the same thing. We have the vector u I plus 1 equals the vector u I plus h times the vector f. So far, so good, everybody? So if you think of this as like a vector, then we have u I plus 1. Okay, that's the index of the iteration, equals ui plus h times f. Okay, so we have almost the same thing, but now we just reviewed the y and the yi plus 1, the yi and the f. They are all vectors. Okay, so here we're talking about vector value functions. So let's look at the example. Example 2 approximates the solution of the previous example over 0, 1 using Euler's method with n equals to 2 subintervals. Okay, so let's copy down what we had before. So what we had. So this is the system. Okay, u1 prime equals u2. Can I copy it? Oh no, I cannot copy it. So u1 prime is u2, u2 prime is u3, u3 prime equals xu3 minus u1 squared minus e to the x. And u1 0 equals 1, u2 0 equals minus 1, u3 0 equals 2. So far so good, everybody? Okay, now we want to look at the interval from 0 to 1. Let's draw it. 0 to 1, and we divide it into two subintervals. Then this is 0.5. Okay, this is x0, this is x1, this is x2. So far so good. In the last chapter we will write y0, y1, y2, but here it's gonna be u vectors. Okay, and so to have the index match, the index should be inside the parentheses. I know this is a little bit confusion. Whenever you write this, it does not mean, see, this is just the index. It's not, even though in this case x0 is 0, but this means u0 is the index of the iteration. Okay? Okay, it's not u of 0, and this guy is not u of 1. You can see this vector, the corresponding x1 is 0.5. It's not 1. So x is not 1. X is 0.5. All right. So let's continue. Okay. So what is h? H is the step size. Usually it's b minus a over n. In this case, is 0.5. Right? Then we're gonna start. So keep this in mind. Oops. Okay. So keep this formula in mind. Let's compute. So first, when I equals 0, x0 equal to 0. Okay. u1 u11. So this is the first coordinate of u1, and second coordinate, and the third coordinate. Okay, what's the first coordinate? Is u1 of 0 plus h. H is 0.5 times f. F, okay, is the u2. So f is u2 of 0. So far so good. Okay, u1 of 0. u1 of 0 is 1. u2 of 0 is minus 1. So we get 1 minus 0.5 is 0.5. So far so good. Okay, next we have u2 of 0 plus 0.5. F, our f is u3. So that's u3 of 0. u2 of 0 is minus 1 plus 0.5. u3 of 0 is 2. 2 times 0.5 is 1. 1 minus 1 is 0. Okay, and f. Oh, this f is more interesting. So it is x0, u3 of 0 minus x0, u1 of 0 square. Let me put the square here. Minus e to the x0. Okay, what is this guy? u3 of 0 is 2, and then x0 is 0. Ooh, nice. And e to the 0 is 1. Oh, so we have 2 minus 0.5 is 1.5. So we get u of 1 is 0.5. Sorry. We can write as a vector. So 0.5, 0, and 1.5. So far, so good? Okay. Next step. When I equals 1. Okay, when I equals 1, u1 of 2 is then similarly just increase the index. So u1 of 1 plus 0.5. See, we just increase the index from the previous formula. Okay, and what is that? u1 of 1 is 0.5 plus 0.5, u2 of 1 is 0. Oh, the answer is 0.5. Okay, and next, u2 of 2 is u2 of 1 plus 0.5, u3 of 1. u2 of 1 is 0. u3 of 1 is 1.5. 1.5 times 0.5 is 0.75. Because it's half of 0.5. Okay? And then u3, let me put it here. Okay, or maybe I just put it here. u3 of 2 is then u3 of 1 plus 0.5. See, it's this guy. Now we increase the index. So this is x1 u3 of 1 minus x1 u1 of 1 squared minus e to the x1. So u3 of 1 is 1.5, and then 0.5 x1 is 0.5, u3 of 1 1.5, x1 0.5, u1 of 1 0.5 squared, e to the 0.5. Okay, so this guy we need a calculator. (1.5) plus 0.5 times 0.5 times 1.5 minus 0.5 cube, right? Cube, and then minus function e to the 0.5. Okay, so the answer is 0.98813. 98813, and then what? 93646. 93646. Okay, great. Because now we get u2 is 0.5 and 0.75. And the next one is 0.9881393 646. So far, so good, everybody? Okay, so that is our answer. Okay, so it's very similar as before, but because we're working with vectors, we have two index. We have the index of the iterations, and we have the coordinates being in the subscript. Okay, so each coordinate at each step, you're gonna do one equation, and then you have to calculate the answer. All right. So keep those in mind. I hope you can work on this example first by yourself, and then you can continue to play the video to check your work. Have you done? Yeah? Okay, let's see. Here we have two variables, u and v. Okay, so let's see. We have the interval is from 0 to 1, and we're using h equals 0.25. Well, it means we're gonna have 4 subintervals. Okay, so that's x0, x1, x2, x3, x4, right? And we're gonna have a vector. So let's see, what's the index? Okay, so we have the vector u of 0, v of 0, and u of 1, v of 1. So be careful, the number in the parentheses, they are the index of the index of the iterations. Okay, they're not the x values. You can see that, for example, here the x values is 0.5. It's not 2. Okay, and u3, we of 3, u of 4, we of 4. Okay, so it will take us 4 steps. So step 1, I equals 0, and then x0 is 0. Okay, now let's see. So keep in mind, our formula, ui plus 1 equals ui plus h times f, right? So u of 1 is u of 0 plus h times f1. f1 is u of 0 plus x0 times v of 0. So far, so good, everybody. U of 0 is 2, h is 0.25. U of 0 is 2, x0 is 0. Oh, 2 times 0.25 is 0.5. 2 plus 0.5 is 2.5. And then we have v1. v1 is v of 0 plus h times our second equations. We have 2u of 0 minus 3x0 v0. v0 is 1, h is 0.25, u of 0 is 2, 3 times 0, oh, so it's gone. So 2 times 2, 4, 4 times 0.25 is 1, right? Because 0.25 is 1 over 4. That times 4 cancel, we get 1. And then there's a 1 in front, so 1 plus 1, the answer is 2. So far, so good. So, oh, this is given. This is 2, 1, right? And then this guy is 2.5 and 2. Alright, so that's the first step. Second step, when I equals 1, x1 equals 0.25. And then u2, what is u2? We're gonna have the same formula, almost the same, but increase the index of the iterations. So u1, so see, we copy down this, but just replace 0 by 1. Okay, now we find the right numbers. u1 is here, 2.5. h is 0.25, u1 is 2.5, x1 is 0.25, v1 is then 2. Okay, 2 times 0.25 is 0.5. 0.5 plus 2.5 is 3. Oh, 3 plus 0.25 is 0.75. And when we add 2.5, that's 3.25. Is that okay, everybody? If you need a calculator, go ahead. Okay, you're allowed to use your calculator in our course. But you gotta write down all the steps, okay? I equals 2, and then, so let me write it down here. Oh, I still have v, I forgot v. Okay, so v2 is then increase the index, u of 1, x1, v of 1. See? It's the same thing, we just increase the index. Now v1 is 2, h is 0.25, u1 is 2.5, x1 is 0.75, v1 is 2. Okay, let's see. 2 times 2.5 is 5. 2 times 0.25 is 0.5. 0.5 times 3, 1.5. Oh, okay. So, let's use our calculator. So, oops. So we have 2 plus 0.25 times 5 minus 1.5 is 3.5. So the answer is 2.875. Okay, so 3.25, 2.875. So far, so good, everybody. Let's change a color. Okay, to make it pretty. I don't know if I keep using the same color. Do you feel bored? Bored. Okay, so all right. Next, I equals 2, x2 is 0.5. Then we have u3. u3 is then, see, we increase the index. u2 plus h, u2 plus x2, v2. u2 is 3.25, h is 0.25, u2 is 3.25, x2 0.5, v2 is 2.875. Okay, so plot this in our calculator. Let's see, 3.25 plus 0.25 times 3.25 and then plus 0.5 times 2.875 close parentheses. Okay, so the answer is 4.421875. 4.421875. Okay, that's u3. Now how about v3? Well, it's gonna be these guys, same thing, increase the index. Okay. Alright, so v2 is 2.875, 0.25, u2 3.25, oops, and then minus 3, x2 is 0.5, and then v2 is 2.875. So far, so good, everybody. And let's see what this number is. So actually, when we calculate it, we can use the previous equations, just change some number. So this is 2.875 plus 0.25 times 2 times that, and minus 3 times 0.5 and 2.875. So the answer is 3.421875. So far, so good. That is the third vector. Okay, so this is 4.421875. It's 3.421875. Okay, last step. I equals 3. x3 equals 0.75. And then we have u4, increase the index, so u3, x3, v3. u3 is 4.421875. h is 0.25. Okay, and u3 4.421875, x3 0.75, v3 3.421875. And what do we get? Let's see here. Okay, so let's see. I want to use this equation, copy here, and then copy this guy, replace it here. This can save me some time. And this is 0.75. Or you can type in the whole thing again, right? You can type the whole thing again. So double check what we type. Yep, that's good. So 6.1689, 6.1689, and then we have 45313. 45313. Okay. Sometimes in this calculation, you can keep 5 decimal places. Okay. So, and this guy, we're gonna increase the index. V3 H 2U3 minus 3X3 V3. V3 is 3.421875 plus 0.25, and then 2U3 is 4.421875, and then minus 3 times 0.75 times 3.421875. Alright, so let's see. Okay, so what do we have now? We can copy it here. Let's copy this guy here. And that number, we copy this guy here and copy here. Here's 0.75, and then is this number copied down here. Okay, so you can also type the whole thing again. Alright, double check what we type. Yep, good. Okay, so the answer is 3.70800. And then we have 7813. 7813. So this is U4. Okay? So U4 V4, this vector equals 6.168945313. The other one is 3.708007813. So far, so good, everybody? Okay, so that is Euler's method. It's very similar to what we did before in last chapter, but now we're working with vectors instead of just a number. Okay? Alright. Just be careful with the indices, okay? Alright, how to use MATLAB. So we can, let's say we want to apply Euler's method with n equals to 10 to this system of ODEs. So U1 prime is U2, U2 prime is U3, U3 prime is x plus 2U1 minus 3U2 plus 4U3 with initial conditions. Okay, first we're gonna define f. So f is the vector value function. So you do f equals inline, and then we have the brackets. Okay, the first one we have U2. So U of 2. 2 is the, oh sorry, abuse of notation. In this case, this 2 is actually the index of the coordinates. Yeah, sorry, a lot of abuse of notation this session. Okay. And then U3, yeah, U3 is U of 3. And then we have x plus 2 times U1 minus 3 times U2 plus 4 times U3. Okay, this is a vector value function. So this is so f is a vector valued function. Okay, and x is the independent variable and u is the dependent variable. Okay, so let me write it down. This is independent variable. So it's a scalar, okay, it's a number, but u is actually a vector. So this is a dependent vector. Okay, it has coordinates u1, u2, u3. Okay, so we can think of u is like u1, u2, u3. Okay, then we have brackets x comma u equals Euler system 6. Okay, so we have the vector value function f, and then here we have, this is the interval. Okay, so this is the interval for x, and then this guy is the initial condition. Vector. Okay, so you can see the initial condition is 4, 3, 2, and we express it as a row vector. And here, because we want to divide it into 10 subintervals, then we put 10 at the end. Okay, and then we want to plot, we can plot the curve, but this is a vector value function. Is hard to plot it, but what it do is it has 3 coordinates. It will give us 3 curves. You can see each coordinate as a function of x, how it looks like. Okay, and you can see here are the vectors. Okay, in the 10 different iterations, intervals. Okay, and these are the coordinate functions. So far, so good, everybody? Okay, let me show you actually how we type it in Octave. So this is Octave, and let's see, this is the syntax, okay? I actually want to type it, okay? Because I don't want to just copy it and paste it here. I want you to see how we actually type it. So F equals inline, parentheses, and then, okay, we have the u of 2, semicolon, u of, I type enter by accident. So let's do it again. U of, I want to type shift in the parentheses, right? So u of 3, and then x plus 2 times. When you do times, you have to use this asterisk. Okay, u of 1 minus 3 times u of 2 plus 4 times u of 3. Okay, and then brackets. So this is a vector value function, and then close it. Sometimes we have to, I haven't closed it, so don't put parentheses yet. We do comma, and then we have the x and the u, okay? Then now we can close. That's F. And then we can do x comma u, brackets, equals Euler sys. Oops. Okay. And then we have F. The interval x is from 0 to 1. And then the brackets, this is the row vector of the initial conditions. So 4, 3, 2. Okay. Yeah, sometimes students confuse. Whoa, which one is the interval? Especially when we have 2 variables, two coordinates, 2 dimensions, okay? Then it looks like a bracket and then 2 numbers in it. Then we get confused. Which one is the interval? Which one is the initial vector? So the first bracket is the x intervals. The second bracket is the initial conditions. Here we do 10 subintervals. Okay. Now you can get those 10 points. Now we can plot those points. So we do x comma u, and then, okay. All right, with, okay, right on. Okay, here we are. We got this. Let me make it bigger. See, we have 3 functions. Those are the coordinate functions. So, we can draw it in space, but here, no matter how, we can have a lot of coordinates, and then it just show up the coordinate functions here. Okay, and let's see if we increase the number of steps. Let's do 100 subintervals. Then and when we plot it, now what happened? You can see the curve is pretty smooth. You see, the curve is pretty smooth. So it's very close to our actual solutions. Okay, when we increase the number of subintervals, the Euler's method approximation is going to be closer and closer. So far, so good. How about let's check our work? Yeah, we can do that. Let's check this guy first. So how do we type it? Why don't you pause the video and try to check it first, and then we can you can continue to play the video, and then we can check it together. Have you done? Let's see. We can go back up and define our f. So define our f. Here we have the first coordinate. So here you think about u1 is u, u2 is v. Then the first one, u plus xv, is like u of 1 plus x times v of v is u of 2. Okay, second one, we have 2 times u. U is u of 1 minus 3 times x times v is u of 2. Okay, and then we only have 2 coordinates, and then xu. Okay, so we have this vector value function, and then we can do Euler system. F, the interval is still 0 to 1, and what is our initial point? Our initial is 2, 1. Okay, and here we divide it into 4 steps. Okay. Does this match with our answer? Does this match? The last one we get these. Does it match? Yeah, see? We get 6.1689, that match. And 3.7080, that match. So we can also use MATLAB to check our work, right? Like when we do our homework problems. And we can also increase the number of subintervals, okay, and we can plot it, and this is what we see, right? We have 2 coordinate functions, and you can see the functions are pretty smooth. Okay, so far so good. Okay, we can also check the previous example. Let's see. Oh, this one. Okay, so this guy, we have f is a vector, but we have 3 coordinates. First coordinate u2, so u2 is u of 2. And then the next one, u3, so u of 3. Okay, sorry about the abuse of notation. And then x times u of 3 minus x times u of 1 square. And then we have, and then minus e to the x, exp of x. Okay, so that is our function. And let's do Euler system. Over the interval still 0 to 1, but the initial points now is 1, comma, minus 1, comma, 2. And here we only use 2 subintervals. Okay, does it match with our answer? Let's see. Yeah, see, 0.5, 0.75, and 0.99 to 1.4. It match. Okay, and you can see when we increase the number, let's do 100 subintervals, and we can plot it again. Then you see, oh, we have 3 coordinate functions, and we can get a very nice curve of each of them. So far, so good, everybody? Okay, so today we talk about the Euler method to solve systems of ODEs. If we have higher order ODEs, we can convert it into a system of first order ODEs and still use the Euler's method to compute. Alright, and that's it for today. Have a nice day. Bye.